Hey everyone, the objective for this video is to address old Regents questions related to the kinetic molecular theory. That's a theory related to gases. So let's first start by looking at some assumptions that we need to make about gases before we can begin. Here they go. Okay, so here are the assumptions for the kinetic molecular theory of gases. So we are talking about particles in a gas move in a random straight line unless they strike something. Then once they strike something, those collisions are perfectly elastic. That means that all the energy that is within the particles are being transferred. So we're really talking about the law of conservation of energy here. Next, the space between the particles compared to the size of the particles themselves is so large that the size of the particles are negligible. Let me demonstrate what that means. That means if this is a particle right here, the next gas particle might be all the way, let's be very dramatic here. Let's just say it's in New Jersey. It's that far away. Now, if we were to look at the distance between this particle here on Long Island and the particle in New Jersey, well, that space is so large, we could just about ignore the size of the particle itself. So that's what this is saying. Again, the space between particles compared to the size of the particle themselves is so large, the size of the particles are negligible. Now, the last one kind of goes with that. There is no intermolecular force of attraction between the particles. And really, how could there be an attraction between the particles if they're that far apart to begin with? Now, a very important thing to realize is that this is trying to describe what's called an ideal gas. Now, no gases are truly ideal. In fact, all the other gases, or all the gases, are really real gases. But this is an ideal situation for us to understand how gases behave. So let's look at some questions. So here's question number one, and let's keep in consideration all of the things we just discussed about the assumptions of ideal gases in the kinetic molecular theory. The question reads, one reason that a real gas deviates from an ideal gas. So we're looking for a reason why they're different. Again, one reason that a real gas deviates from an ideal gas is that the molecules of a real gas, what do molecules of a real gas do different than an ideal gas? Straight line motion? No, they both have particles moving in a straight line motion. No net loss of energy on collision. Well, that means that they're perfectly elastic. Law of conservation of energy, both of them follow this rule. A negligible volume of the particles. No, that holds true for both. Or forces of attraction for each other. Now that is our answer, and let me describe it for you. You see, in an ideal gas, let's just put that at ideal gas versus a real gas. The ideal gas is as the particles are moving around, well, they will not be attracted to one another. When in fact the reality is when those gas particles do move around, they sometimes come in close proximity to one another, that there is a force of attraction realized. So in a real gas, we will have forces of attraction. But again, kinetic molecular theory tries to identify the perfect situation to first understand how gases behave. So once again, the answer is 4. Number 2, an ideal gas is made up of gas particles that have volume. Well, remember, the particles, the size of them is negligible, so we ignore the volume of the particles themselves. Can be liquefied. Okay. Don't really understand what they mean by that. Attract one another, which is what 3 says. No intermolecular forces of attraction for ideal gases. Or are in random motion? Yes, random straight line motion. It is choice 4. All right, number 3. As space between the molecules in a gas sample decrease, the tendency for the behavior of the gas to deviate from the ideal gas laws. So what we're saying here is these particles, okay, if they are spread apart such as this, well, what's going to happen when they start getting closer and closer together? Well, it turns out that as they get closer and closer together, the tendency for them to attract to one another is going to increase. So therefore, let's read this again so I answer it correctly. Okay. As the space between the molecules in the gas sample decreases, the tendency for the behavior of this gas to deviate from the ideal gas law, well, it will increase because it's more likely that it's going to deviate from that. In fact, if you push them close enough together, they might actually even become a liquid. Number 4. The behavior of a real gas would be most similar to the behavior of an ideal gas under conditions of, well, if you do scan these choices, both of them deal with pressure and temperature. So what we're looking for is a situation that would make these particles kind of go further apart from each other and decrease the chance of them attracting to one another. Now I do know that if I were to add pressure, well, think of maybe a balloon full of gases, and if I added pressure to a balloon from all sides, the balloon itself would shrink and the particles inside would get closer together. So again, I'm adding pressure to the balloon, I'm squeezing it, so the particles are going closer together. So if adding pressure brings the particles closer together, related to pressure, what would bring them further apart? Well, if I decrease pressure. So I am looking so far at choice 3 or 4 because it talks about lowering pressure. Now, what can I do temperature-wise to make particles spread apart more? And we do know that that would be increased temperature. So the answer is choice 3. Number 5. 5 has it's a two-part question. There's an A and a B, so we'll tack A first. And it says 4 identical balloons contain equal volumes of gas at STP. The key is this term, equal volumes. We have balloon 1 with H2 gas, balloon 2 with helium gas, 3 with oxygen gas, and 4 with nitrogen gas. And it asks which balloon, if any, would weigh the most. And you need to explain. So what we're looking at is 1, 2, 3, 4 balloons, 1 with hydrogen gas, 1 with helium gas, oxygen gas, and nitrogen gas. And the key again is it says equal volumes. Now if they have equal volumes, there's something known as Avogadro's, and I think I may have spelt it wrong. Forgive me for that. Hypothesis, which states that if you have equal volumes of a gas, you have equal number of particles. So hypothetically, I can say that I have 1 mole of each of these gases. Now, if I have 1 mole of H2, I can figure out what its mass is. If I have 1 mole of helium gas versus 1 mole oxygen gas and 1 mole of nitrogen gas. Now let me go ahead and bring up something you're familiar with to assist us. And let's look at the masses for each of these. Straighten this out. The mass for hydrogen is rounded to be 1. The mass for helium is rounded to be 4. For nitrogen it's 14 and oxygen 16. So let's actually do the math on this. Okay, we've got 2 hydrogens, each with a mass of 1 AMU. I'll put AMU up top. Or we actually could say grams per mole, seeing that we're talking about moles here. And the mass for 1 mole, or that balloon full of hydrogen, is 2 grams. Well, 2 grams. Helium, we said that the mass was 4. There's 1 helium times 4 is equal to 2. We said the oxygen, its mass was 16. So 2, because of 2 oxygens, 2 times 16 is equal to 32. And what was nitrogen again? Let me pull it up. Nitrogen's was 14. So get that off of there. So 2 times 14 is equal to 28. So which one of these has the greatest mass? It would be oxygen. And the explanation would have to go and describe how, because of Avogadro's hypothesis, each of the balloons have the same number of particles, and when you examine the mass of each of these particles, O2 having 2 oxygens in each particle, each weighing 16 grams per mole, with a grand total of 32 grams, compared to the others, is the heaviest. Alright, number 5b, same scenario, but this time it's saying, according to the kinetic molecular theory, why would the balloons expand if they were heated? Well, if they were heated, the particles themselves would be moving faster, therefore decreasing even the smallest amount of intermolecular forces, asking the particles, in a sense, to try to escape even further. So, as the particles are heated, they gain more energy and move faster. That would most certainly get you the credit necessary for this question. And last, the kinetic molecular theory assumes that particles of an ideal gas. Now we're rolling back to our assumptions that we had before, and we're looking for the one that matches. Number 1 says are in random, constant, straight line motion. That looks really good, but let's look at the others just in case. Are arranged in a regular geometric pattern? No, because that would describe a solid. Have strong attractive forces between them? No, again that would relate to a solid, maybe even a liquid. And number 4, have collisions that result in a system losing energy? Well, that defeats the law of conservation of energy. So it confirms number 1 is our choice. I hope these questions helped. Have a good day.